Okay, let's dive right into this explainer. Today, we're looking at something I find absolutely fascinating, which is the journey of raw, messy data and how it transforms into an absolute predictive powerhouse. We hear a lot about machine learning models and AI, right? But the secret sauce, the real hero of the story here, is what happens before the machine ever starts learning. Specifically, we're going to explore how feature engineering makes it possible to stop credit card fraud dead in its tracks.
So, here is our roadmap for today. We'll start with the fraud prediction problem, define feature engineering, explore our raw dataset, engineer the features, train with AutoML, and finally, evaluate the model's performance.
Section 1. The Fraud Prediction Problem. Finding the needle in the data.
The primary business goal for financial companies is pretty clear-cut. Develop a predictive classifier model that accurately spots credit card fraud in real time or even in batch predictions to protect their bottom line. But here's the massive challenge. How do you predict fraud from millions of perfectly normal, everyday transactions? It is quite literally the ultimate needle in a haystack scenario.
And this number brilliantly illustrates just how tiny that needle actually is. 492. In the raw dataset we're looking at today, which was provided by Kaggle and analyzed by researchers in a Google Cloud environment, out of over 284,000 total transactions, there were only 492 instances of actual fraud.
You can see the visual impact of this massive class imbalance right away. That giant column represents the hundreds of thousands of legitimate transactions, and that virtually invisible sliver on the right, that's our fraud cases. If you just feed this raw data into a machine learning model as is, well, the model's probably just going to guess not fraud every single time. It'll be technically accurate 99.8% of the time while completely failing its actual business purpose. So we need an intervention.
Which brings us to Section 2. What is feature engineering? The hero of the ML pipeline.
Before our model can actually learn anything, we have to step in. Feature engineering is essentially the art of converting raw data into useful input variables or features that improve the performance of our machine learning models. Because even the most advanced algorithms out there can completely fail if they're trained on poorly designed features. Good feature engineering improves accuracy, it reduces overfitting, and it basically wrangles the messy reality of raw data.
So it's absolutely crucial to understand the difference between good and bad feature engineering. Bad feature engineering ignores missing values, includes wild outliers, or actually even worse, it just feeds the model's raw timestamps. Good feature engineering, on the other hand, handles missing values carefully. It scales numerical variables, and it transforms those raw timestamps into something useful, like categorizing a transaction by the day of the week or hour of the day. It's really all about designing data that aligns with domain knowledge so the model can actually pick up on the underlying patterns.
Let's move to Section 3, Exploring the Raw Data, Assessing the Battlefield.
You can't fix what you don't understand, right? So the researchers started by loading the raw dataset into a Google Cloud storage bucket. Their initial exploration steps were highly systematic. They identified the variables, they examined data types to see if anything needed converting, they checked for any missing values across the entire board, and they ran correlation analysis to see exactly how these variables were interacting with each other.
And here is one of the absolute rarest sights in all of data science. Checking for missing values revealed 0 missing entries across every single column. That never happens. Usually, handling missing data is a massive headache and a huge part of feature engineering, using techniques like mean imputation. But the data here was perfectly intact, which let the researchers totally bypass missing value imputation. But their correlation analysis did uncover something critical. They found that a feature labeled V2 was highly correlated with the transaction amount variable. In feature engineering, keeping highly correlated, redundant features is a bad idea. It's like having two people shouting the exact same instructions. It can confuse the model and make training way less efficient. So, a strategic decision had to be made.
That takes us to Section 4, Engineering the Right Features, Shaping the Solution. So here's exactly what the researchers did to transform the data. Step 1. They just dropped feature V2 completely to eliminate that redundancy we just talked about. Step 2, they split the data into training and test sets, holding back a random 10% of the original unbalanced data to serve as a real-world test later on. And Step 3, this is the most vital part of the whole operation, they completely restructured the training data to fix that massive class imbalance. The result of that balancing act is a real game changer. They built a custom training dataset that kept 90% of all those rare fraud cases, and then they randomly sampled just enough normal, non-fraud transactions to match it. This gave them a tightly balanced training dataset of just 1,100 rows, exactly 437 fraud cases and 663 non-fraud cases.
By leveling the playing field like this, they prevented the model from simply taking the lazy route and specializing in predicting non-fraud.
Section 5. Training with AutoML, letting the machine learn.
Now, armed with a perfectly engineered and balanced dataset, the researchers followed Google's machine learning best practices. Because they needed efficiency, they handed the training process over to Google Cloud's AutoML. They chose AutoML because it completely automates model selection, it handles all the complex hyperparameter tuning, and it manages cross-validation totally on its own. It's basically letting the machine do the heavy lifting.
Jumping into the Vertex AI interface, the researchers define their objectives strictly as classification. Makes sense, right? Our goal isn't to predict a continuous number like a house price. We need to categorize transactions into very distinct buckets. It's either fraud or it's not fraud.
And to pull that off, the model needs a bullseye. So the target column is set to the class variable. That's the column that holds the definitive answer of whether a past transaction was legitimate or fraudulent. The model's job is to analyze all the other engineered features to figure out exactly how to hit that target.
Finally, Section 6. Evaluating model performance, the final verdict. So, moment of truth. Did all this careful data prep actually work? The model was tested against that independent 10% test set we set aside earlier, and the resulting confusion matrix is pretty incredible. The model successfully predicted 100% of the non-fraud cases correctly. It didn't falsely accuse a single legitimate customer of fraud.
And what about the actual fraud cases? It correctly detected 91% of them. Now, in the machine learning world, getting 100% on one class and 91% on the other during training evaluation can sometimes be a classic symptom of slightly overfitting the data, meaning the model might be just a bit too closely tuned to its training set. But the researchers noted that given their time constraints, this was an incredibly strong performance, and they accepted the model as a clear win.
And this brings us to the ultimate payoff of feature engineering: feature importance. This shows us exactly which variables the machine relied on most heavily to make its predictions. Check out that top bar. Feature V14 was overwhelmingly the most important predictor in separating fraud from normal transactions. Because they dropped redundant features like V2 and properly balanced the classes, the model was able to clearly see the massive signal coming from V14.
It just goes to show that the true power of a machine learning model isn't just the fancy algorithm, it is entirely in how carefully you craft the data you feed it. So I'm going to leave you with this. Looking at your own business, your own projects, what messy, unstructured data sets are you sitting on right now? And how could strategic feature engineering unlock predictive value that you didn't even know was there? Thank you so much for joining me for this explainer, and I hope this sparks some awesome ideas for your next data project.